Could the very fabric of your reality be composed of tiny vibrating strings hidden in dimensions we're only now beginning to prove exist? For 50 years, string theory has been called the most beautiful idea in physics and the most frustrating. No evidence, no proof, just elegant mathematics describing a universe we can't see. Until April 2025, when astronomers observed something that might change everything. Could the theory of everything finally be real? Welcome to Sleep Entangled, where the deepest mysteries of physics and the tranquility of contemplation merge into nocturnal voyages. If you find wonder in these explorations of reality's hidden fabric, remember to subscribe and let curiosity guide your nights. Now, settle in, breathe slowly, and let's drift together through the most ambitious theory humanity has ever conceived. In 1955, Albert Einstein died with unfinished calculations scattered across his desk at Princeton. For the last 30 years of his life, he had pursued a single goal, a unified field theory that would merge gravity with electromagnetism, explaining all forces of nature in one elegant mathematical framework. He never found it. But Einstein's dream didn't die with him. It evolved. It became grander, more ambitious, stranger. Today we call this quest string theory, and it promises not just to unify forces, but to reveal the fundamental fabric of reality itself. The question that has haunted physics for a century is simple to state, but maddeningly difficult to answer. How do we reconcile quantum mechanics, which governs the smallest scales of existence, with general relativity, which describes gravity and the cosmos? Quantum mechanics tells us that particles are probabilistic, existing in superpositions, behaving according to uncertainty. General relativity tells us that space-time is smooth, continuous, predictable, a geometric stage upon which matter and energy dance. But these two pillars of modern physics don't fit together. When you try to apply quantum rules to gravity, the mathematics explodes. Infinities appear everywhere. The equations break down. Something is missing. For decades, physicists have searched for a theory of quantum gravity, a framework that would make sense of both the quantum and the cosmic, explaining how gravity emerges from the quantum realm. String theory is the leading candidate, but here's the challenge. For 50 years, string theory has remained purely mathematical. Beautiful, elegant, perhaps the most sophisticated structure ever conceived by the human mind, but untestable. No experiment could probe the tiny scales where strings supposedly vibrate. No observation could confirm or deny its predictions. Critics have been brutal. They call it not even wrong, meaning it makes no falsifiable predictions. It's mathematics, they say, not physics. A beautiful dream disconnected from reality. Yet, in 2024 and 2025, something shifted. A series of breakthroughs, both theoretical and observational, have brought string theory closer to experimental validation than ever before. The mathematics proved more constrained than anyone realized. Dark energy, the mysterious force accelerating the universe's expansion, began showing behaviors that string theory had predicted, and physicists found ways to test the theory's consequences in particle accelerators and astronomical observations. After half a century in the wilderness, string theory might finally be emerging into the light, and to understand why this matters, why physicists have invested so much in an idea that seemed untestable, we must first understand what string theory actually proposes. What are these strings? Why do they require extra dimensions? And how could they possibly explain everything from gravity to electrons to the very structure of space-time? Imagine for a moment that you could zoom into the fabric of reality, past atoms, past protons and neutrons, past quarks and electrons down to the smallest possible scale, the Planck length, about 10 to the minus 35 meters, a scale so tiny that it makes an atom look like a galaxy. At this scale, according to string theory, particles are not points. They are tiny, vibrating loops of energy, strings. Everything in the universe, from light to matter to gravity, is made of these strings vibrating in different patterns. A photon is a string vibrating one way, an electron vibrates another way. A graviton, the hypothetical quantum of gravity, vibrates in yet another pattern. It's like music. The same violin string, depending on how it's played, produces different notes. In string theory, the universe is a cosmic symphony, and every particle is a note played by the vibrating strings of reality. This is the central insight of string theory, that the diversity of particles and forces we observe emerges from a single, unified substrate, strings, vibrating in a space with more dimensions than we can see. But here's where things get strange. For the mathematics of string theory to work, space-time cannot have just the 3 dimensions of space and one of time that we experience. It must have 10 dimensions, or in some versions, 11. Where are these extra dimensions? String theory answers. They're here, all around us, but curled up so small, compactified at the Planck scale, that we can't perceive them. Imagine an ant walking on a tightrope. From far away the rope looks one-dimensional, just a line. But to the ant the rope's surface is 2-dimensional. It can walk around the rope's circumference as well as along its length. String theory proposes that reality is similar. We perceive 3 spatial dimensions because they are large, but 6 more dimensions exist, curled into shapes so tiny that even atoms don't notice them. Only strings, vibrating at the Planck scale, interact with these hidden dimensions. The specific shape of these extra dimensions, a class of geometric structures called Calabi-Yau manifolds, determines the physics we observe. Different shapes produce different particles, different forces, different constants of nature. This is both the promise and the curse of string theory. It's elegant. One framework, one fundamental object, the string. One set of rules. But it's vast. With so many possible ways to curl up the extra dimensions, string theory seems to predict not one universe, but 10 to the power of 500 possible universes. A landscape of possibilities so enormous that finding our universe within it feels like finding a single grain of sand on an infinite beach. And yet, recent breakthroughs suggest that this landscape might not be as arbitrary as it seems. The mathematics of string theory, when carefully constrained, might narrow the possibilities dramatically. As you rest tonight, imagine the strings that, according to this theory, compose your body, your thoughts, the air you breathe. Tiny loops of energy, vibrating patterns weaving reality into existence, dimensions curled so tight that they hide from view, yet shaping everything you experience. Einstein's dream has grown into something far stranger and more beautiful than he could have imagined. But is it real? Or is it merely the most exquisite illusion mathematics has ever conjured? In the chapters ahead, we'll explore this question, following the evidence, the criticisms, the breakthroughs, and the tests that might finally answer whether string theory describes our universe or merely a beautiful fiction. Chapter 2. What are strings? The music of reality. Let us slow down and picture what string theory actually proposes at its most fundamental level. Traditional physics since the ancient Greeks has asked, what is matter made of? Democritus suggested atoms, indivisible particles. For centuries, atoms were thought to be the smallest units. Then we discovered that atoms have structure, electrons orbiting nuclei. Then we found that nuclei are made of protons and neutrons. Then we discovered that protons and neutrons are made of quarks. At each level, we found a deeper layer. But we also assumed that eventually we'd reach the bottom, truly fundamental particles with no internal structure, point-like and irreducible. The standard model of particle physics takes this approach. It describes particles like electrons, quarks, and photons as zero-dimensional points. They have no size, no structure, just properties, mass, charge, spin. This model is extraordinarily successful. It predicted the Higgs boson decades before it was discovered. It describes 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, with breathtaking precision. But it has a glaring problem. Gravity doesn't fit. When you try to add gravity to the standard model, treating it as quantum field like the others, the mathematics fails. Infinities plague the calculations, and no amount of clever tricks can tame them. This is where string theory enters. String theory proposes that the fundamental constituents of reality are not points, but one-dimensional objects, strings. These strings are unimaginably small, vibrating at the Planck length, about a billionth of a billionth of a billionth of a billionth of a centimetre. At this scale, the strings can be open, like a line segment with 2 endpoints, or closed, forming loops. They vibrate, oscillate, resonate, and each vibrational mode corresponds to a different particle. Imagine a guitar string, pluck it, and it vibrates in a certain pattern, producing a note. But it can also vibrate in harmonics, higher frequencies, overtones. The same physical string produces different sounds depending on how it vibrates. In string theory, this is how particles work. An electron is a string vibrating in a particular mode. A photon is a different mode. A quark is yet another. The diversity of particles in the standard model emerges from a single type of string, vibrating in different patterns. This is deeply elegant. Instead of dozens of fundamental particles, each requiring its own explanation, string theory offers one fundamental object, the string. Everything else is music played upon it. But here's where the theory becomes more constrained and more interesting. The mathematics of string theory is rigid. You can't just propose strings and be done. The equations demand specific conditions. First, they demand supersymmetry, a mathematical symmetry relating particles of different spins. For every boson, a force-carrying particle, like the photon, there must be a corresponding fermion, a matter particle, like the electron, and vice versa. These superpartners have not been observed, which is one reason physicists are skeptical, but string theory requires them. Second, the equations demand extra dimensions. You can't have strings vibrating in just 4-dimensional spacetime. The math doesn't work. You need 10 dimensions, 9 of space, 1 of time, or in M theory, a generalization of string theory, 11 dimensions. Why 10 or 11? The answer lies in quantum anomalies, mathematical inconsistencies that would make the theory meaningless. These anomalies cancel out only in specific dimensions. For string theory, the magic number is 10. This requirement of extra dimensions seemed absurd when first proposed in the 1980s. But physicists asked, if these dimensions exist, why don't we see them? The answer is compactification. Imagine a garden hose. From far away it looks one-dimensional, just a line. But if you were an ant walking on it, you'd discover a second dimension, the hose's circumference. That dimension is curled up, hidden from distant observers. String theory proposes that 6 of the 9 spatial dimensions are compactified in a similar way. They're curled into tiny geometric shapes called Calabi-Yau manifolds, so small that even subatomic particles don't notice them. The specific shape of these manifolds is crucial. It determines which particles appear in the low-energy world we observe. It determines the masses of particles, the strengths of forces, the constants of nature. Think of it like this. The strings are instruments. The extra dimensions are the concert hall. The shape of the hall, its acoustics, affects how the music sounds. In string theory, the sound is the physics we observe. Calabi-Yau manifolds are named after mathematicians Eugenio Calabi, who conjectured their existence, and Xingtung Yau, who proved they exist in the 1970s. These are 6-dimensional shapes with special geometric properties. They're compact, complex, and have a particular kind of symmetry that makes them compatible with supersymmetry. But here's the problem. There are many possible Calabi-Yau manifolds. Estimates suggest there could be hundreds of thousands or more. Each one would produce a different universe with different physical laws. This is the string landscape, a vast space of possible vacua, each corresponding to a different way the extra dimensions could be curled up. In principle, 10 to the power of 500 different universes could exist within string theory's framework. This is troubling. Science aims to explain why the universe is the way it is. But if string theory predicts 10 to the power of 500 possibilities, how can it explain anything? It seems to predict everything and nothing at the same time. Some physicists embrace the landscape. They invoke the anthropic principle. Perhaps all these universes exist somewhere in a vast multiverse, and we observe the one we do because it's compatible with life. If the constants of nature were slightly different, we wouldn't be here to ask why. Others found this deeply unsatisfying. Leonard Susskind called it a predictive disaster. String theory, they argued, had become untestable, not because we lacked the technology, but because it made so many predictions that no single experiment could rule it out. But in 2024 and 2025, something changed. Physicists discovered that string theory is more constrained than previously thought. Not all of those 10 to the 500 possibilities are actually viable. Many lead to mathematical inconsistencies or violate fundamental principles. The swampland of impossible theories, it turns out, is vast, and the island of consistent theories is much smaller. A playful thought. Imagine you're exploring a vast library with 10 to the power of 500 books. At first it seems hopeless to find the right one, but then you discover that most books are blank or gibberish or self-contradictory. Only a tiny fraction contain coherent stories. Suddenly, the search becomes manageable. This is what's happening in string theory. The landscape is shrinking. The theory is making definite predictions, and remarkably, some of these predictions are starting to match observations. So, as you rest, let this image settle. Reality woven from vibrating strings, tiny loops of energy dancing in 10 dimensions. 6 of those dimensions hidden, curled into shapes we can't see, but that determine everything we experience. The universe as a symphony, and we are notes in the music. In the next chapter, we'll confront the harshest criticisms of string theory and see how recent breakthroughs are beginning to answer them. Chapter 3. The Critics Strike. Why String Theory Seemed Doomed. No scientific theory has inspired as much passion and as much controversy as string theory. For decades, it was the dominant framework in theoretical physics, attracting the brightest minds, dominating conferences, shaping careers. but it also became a target. Critics argued that it had become more philosophy than physics, more mathematics than science. The criticism centers on a fundamental principle of science: falsifiability. A theory, according to philosopher Karl Popper, must make predictions that can be tested and potentially proven wrong. If a theory can accommodate any observation, it's not science, it's metaphysics. String theory, critics argued, failed this test. Peter Woit, a mathematician at Columbia University, wrote a book titled Not Even Wrong, arguing that string theory makes no testable predictions. Lee Smolin, a physicist and proponent of loop quantum gravity, a rival approach to quantum gravity, wrote The Trouble with Physics, accusing string theory of monopolizing resources and suppressing alternative ideas. Their criticisms were sharp. String theory, they said, had become a sociological phenomenon, a belief system held by a community of physicists who had invested their careers in it, rather than a scientific theory grounded in evidence. Let's examine their arguments fairly, because they are not trivial. First, the problem of scale. Strings, if they exist, vibrate at the Planck length, about 10 to the negative 35th meters. This is incomprehensibly small. To probe this scale directly would require a particle accelerator the size of the Milky Way galaxy. We will never build such a machine. So how can string theory ever be tested? Second, the landscape problem. With 10 to the power of 500 possible vacua, string theory seems to predict every possible universe. If dark energy had been twice as strong, string theorists could point to a vacuum that predicts that. If electrons were heavier, they could find a vacuum for that too. The theory, critics argued, was so flexible that it could never be wrong, which means it can't be science. Third, the lack of supersymmetry. String theory requires supersymmetry, but no superpartners have been found. The Large Hadron Collider, the world's most powerful particle accelerator, has searched for them extensively. Nothing. If supersymmetry doesn't exist in nature, string theory collapses. Fourth, the absence of gravitons. String theory predicts that gravity is mediated by particles called gravitons, just as electromagnetism is mediated by photons. But gravitons are extraordinarily difficult to detect. Gravity is so weak that individual gravitons barely interact with matter. We may never observe one directly. Fifth, string theory has made no unique, confirmed predictions. The Standard Model predicted the Higgs boson. When it was discovered in 2012, the model was vindicated. General relativity predicted gravitational waves. When they were detected in 2015, Einstein was proven right again. What has string theory predicted that was later confirmed? Critics said, nothing. These are serious challenges. For a while, it seemed string theory might fade away, a beautiful mathematical structure admired for its elegance but ultimately disconnected from physical reality. But string theorists had responses. First, they argued that indirect tests are possible. Just because we can't probe the Planck scale directly doesn't mean we can't test string theory's consequences. Cosmology, black hole physics, and high-energy particle collisions might reveal signatures of string theory without requiring Planck scale experiments. Second, they pointed out that the landscape, while vast, might be navigable. Not all vacua are equally likely. Perhaps there are principles, anthropic, statistical, or yet undiscovered, that select certain regions of the landscape. And even if the landscape is large, that doesn't mean string theory makes no predictions. It might just mean we need to understand which vacuum describes our universe. Third, they noted that supersymmetry might be broken at higher energies than the LHC can reach. Just because we haven't found superpartners yet doesn't mean they don't exist. Future colliders might discover them. Fourth, they emphasize that string theory's consistency is itself remarkable. Many quantum gravity theories fail mathematically. They produce infinities, inconsistencies, or contradictions. String theory is one of the few frameworks that works mathematically. That alone suggests it might be on the right track. And fifth, most importantly, string theorists pointed to the December 2024 breakthrough that changed everything. A team of physicists at Caltech and New York University, led by Clifford Chung, Aaron Hillman and Grant Remen, published a paper in Physical Review Letters that used a technique called bootstrapping to show that string theory emerges as the unique solution to certain consistency requirements. Bootstrapping is a method of constructing theories from first principles, demanding only that they obey basic physical laws like unitarity, probabilities sum to 1, and causality, causes precede effects. The researchers asked, if we impose these fundamental requirements on a theory of quantum gravity, what do we get? The answer, string theory. Not one of many possibilities, but the only possibility that satisfies the constraints. Grant Remen stated, "This paper provides an answer to this string theory question for the first time." The mathematics showed that string theory isn't arbitrary, it's inevitable, given certain assumptions about how quantum gravity should behave. This is a game changer. It suggests that string theory isn't just a beautiful guess, but a consequence of deeper principles. It's not that physicists chose string theory. It's that the universe, if it's quantum and includes gravity, must be described by something like string theory. But the biggest shift came in April 2025, when astronomers released data that seemed to support one of string theory's core predictions. Critics have long demanded, give us a prediction. Something specific, something we can test. String theory did. And in 2025, the universe answered. As you drift deeper into stillness, consider this. Science progresses not by perfection, but by confrontation. Theories are tested by skeptics, sharpened by criticism, and ultimately judged by evidence. For 50 years, string theory faced withering critique, but it survived, not because its proponents were stubborn, but because the mathematics held together and the theory adapted. Now, with bootstrapping showing its inevitability and observations beginning to support its predictions, string theory is entering a new phase. The question is no longer, can it be tested, but what will the test reveal? In the next chapter, we'll explore the evidence that emerged from one of the universe's most mysterious phenomena, dark energy, and the observation that sent shockwaves through physics. Chapter 4. April 2025. The Dark Energy Discovery. On April 4th, 2025, the Dark Energy Spectroscopic Instrument Collaboration, known as DESI, released results that stunned the physics community. For years, cosmologists have known that the universe is expanding and that this expansion is accelerating. Some mysterious force, dubbed dark energy, is pushing galaxies apart faster and faster. Dark energy makes up about 68% of the universe's total energy, yet we don't know what it is. The simplest explanation is Einstein's cosmological constant, a fixed energy density filling all of space. If dark energy is a cosmological constant, its strength should remain the same throughout cosmic history. But DESI found something different. By mapping millions of galaxies across billions of years of cosmic time, they discovered that dark energy's influence appears to be changing. It seems to be weakening slightly over time. This might not sound dramatic, but it's huge. A cosmological constant, by definition, doesn't change. If dark energy is weakening, it's not a simple constant. It's something dynamic, evolving, possibly tied to deeper physics. And here's where string theory comes in. Within days of the DESI announcement, physicists at Virginia Tech, the State University of New York, and the University of the Witwatersrand in South Africa published a preprint arguing that string theory naturally predicts this behavior. They proposed that dark energy arises from the geometry of the extra dimensions in string theory. As the universe expands, these hidden dimensions subtly change shape, affecting the strength of dark energy. The result: dark energy that evolves over time, weakening as the universe ages, exactly what DESI observed. One of the authors stated, "Given our proposal for the origin of dark energy from the geometry of the dual spacetime, the latest results from DESI might point to a fundamentally new understanding of quantum spacetime in the context of quantum gravity." Let that sink in. For 50 years, string theory had no observational support. Now, one of the most fundamental mysteries in cosmology, dark energy, might be its first confirmed prediction. Of course, skepticism remains. Other physicists caution that DESI's data, while intriguing, isn't yet conclusive. The measurements have error bars. Other models might explain the observations. Independent confirmation is needed, but even skeptics admitted this is the closest string theory has ever come to making contact with observation. To understand why this matters, we need to explore what dark energy is and why its evolution is so significant. In 1998, two teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, discovered that distant supernovae were fainter than expected. This implied that the universe's expansion wasn't slowing down as gravity would suggest, but speeding up. This was baffling. What could cause the universe to accelerate? The answer, they realized, was some form of energy filling empty space. Dark energy. Einstein's equations allow for such energy, represented by the cosmological constant, usually denoted by the Greek letter lambda, L. Einstein originally introduced it to keep the universe static, then abandoned it when he learned the universe was expanding. But in 1998, it returned. The cosmological constant has a peculiar property. Its energy density doesn't dilute as space expands. Imagine filling a box with gas. If you expand the box, the gas spreads out, becoming less dense. But dark energy doesn't dilute. As the universe grows, the amount of dark energy grows proportionally, maintaining constant density. This leads to accelerated expansion. The more space there is, the more dark energy there is, driving even faster expansion in a runaway process. For decades, the cosmological constant seemed to fit observations perfectly. But it has a deep theoretical problem. Why does it have the value it does? Quantum field theory predicts a cosmological constant, but 120 orders of magnitude larger than observed. This is the worst prediction in physics. String theory offers a potential resolution. In string theory, the cosmological constant isn't a fundamental parameter. It's determined by how the extra dimensions are compactified. Different Calabi-Yau shapes produce different values. Perhaps our universe has the shape that produces the tiny cosmological constant we observe, but there's a subtlety. Pure string theory, in its simplest form, struggles to produce stable vacua with a positive cosmological constant, which is what we observe. Most vacua have 0 or negative values. This limitation is called the Swampland Conjecture, proposed by Kumran Varfa and others. The swampland is a metaphor. The landscape of string theory contains possible universes, but many of these are actually inconsistent. They lead to instabilities or contradictions. These live in the swampland. Only a smaller subset of universes are on solid ground. The landscape proper, One Swampland criterion states that in any viable theory, the potential energy of scalar fields must obey certain slope conditions. If dark energy is dynamical, changing over time, it falls within these conditions. If it's a cosmological constant, fixed forever, it might not. This led to a puzzle. The Swampland seemed to rule out universes with a cosmological constant like ours. Either the Swampland conjecture was wrong, or something subtle was happening. DESI's observation might resolve this. If dark energy isn't a cosmological constant, but instead a slowly evolving field called quintessence, then it fits naturally within string theory's framework. The Swampland criteria allow dynamical dark energy, so the DESI result did two things. It suggested dark energy isn't constant, and it aligned with string theory's predictions. To keep it fun, imagine you're watching a movie. For most of the film, you assume the projector is running at constant speed, but then you notice the action slowing slightly. You realize the projector is winding down. This tiny change reveals something about how the projector works, information you couldn't have guessed from constant speed alone. Dark energy's evolution is similar. Its subtle weakening over billions of years reveals something about the mechanism driving it, pointing towards string theory's dynamical extra dimensions rather than a fixed cosmological constant. But caution is warranted. Science history is filled with premature celebrations. Anomalies appear, then vanish with better data. Alternative explanations emerge. The path from intriguing observation to confirmed theory is long and uncertain. Still, for string theorists, this is the most exciting development in decades. After years of criticism that the theory was untestable, they can now point to an observation and say, string theory predicted this. As you close your eyes, imagine the hidden dimensions of reality, curled so small we can't see them, yet subtly affecting the larger scales, the expansion of the entire universe. Dark energy, the mysterious force accelerating cosmic growth, emerging from the geometry of spaces we can't perceive. And imagine physicists, after 50 years of mathematical exploration, finally finding a thread connecting their elegant equations to the real universe we inhabit. In the next chapter, we'll explore another 2025 breakthrough, one that solved a problem that had plagued string theory for years and opened the door to new possibilities. Chapter 5. March 2025. Escaping the Swampland. In March 2025, physicist Eduardo Guendelman published a paper in the European physical journal C that offered a radical solution to one of string theory's deepest puzzles: how to escape the Swampland. To understand the breakthrough, we need to grasp the Swampland Conjecture, a set of criteria proposed in the mid-2000s by Qumran at Harvard and colleagues. The idea is simple but profound. Not all mathematical theories are physical. Just because you can write down equations doesn't mean they describe reality. Some theories, when examined closely, contain hidden inconsistencies or pathologies. These live in the Swampland, a metaphorical region of theory space where the terrain is unstable. The Swampland Conjecture provides guidelines for distinguishing viable theories, the landscape, from non-viable ones, the Swampland. One key criterion involves scalar fields, quantum fields associated with particles like the Higgs boson or hypothetical inflatons that drove cosmic inflation. The criterion states, in any consistent quantum gravity theory, the potential energy of scalar fields must satisfy certain slope conditions. Roughly speaking, the potential can't be too flat. It must drop steeply enough that, if rolled down, the field changes rapidly. Why does this matter? Because a cosmological constant corresponds to a perfectly flat potential. a field sitting at a constant value forever. If the potential must have a slope, then a true cosmological constant might not be allowed in string theory. This created a dilemma. Observations suggest our universe has a positive cosmological constant, or something very close to it. But string theory, according to the Swampland Conjecture, struggles to produce one. The obvious resolution was that dark energy isn't a cosmological constant, but something dynamical, a field slowly rolling down a potential. This would satisfy the Swampland criteria, but constructing explicit models was difficult. Enter Eduardo Gwendelman's breakthrough. Gwendelman proposed a new class of string models where the string tension, the energy per unit length of a string, is not fixed, but generated dynamically through internal mechanisms. Think of it this way. Normally, string theory assumes strings have a fundamental tension, like guitar string with a set tightness. But Gwendelman suggested that this tension could emerge from the string's interactions with other fields. This subtle shift has profound consequences. With dynamical string tension, the theory gains new degrees of freedom. The extra dimensions can evolve in ways previously thought impossible. And crucially, this allows for stable vacua with properties matching our universe, including a slowly evolving dark energy that satisfies Swampland criteria. The paper demonstrated that inflation, the rapid exponential expansion, thought to have occurred in the universe's first fraction of a second, could also be realized naturally in this framework. Inflationary models typically struggle in string theory because they require flat potentials, which the Swampland forbids. But with dynamically generated tension, inflation becomes possible without violating Swampland rules. This work represents a conceptual breakthrough. For years, the Swampland seemed to limit what string theory could predict, ruling out universes like ours. But Gwendelman's approach shows that by relaxing a foundational assumption that string tension is fixed, new pathways open. The implications extend to cosmology. If dark energy arises from dynamical string tension, its evolution over time is a natural prediction. The DESI observations showing weakening dark energy fit this picture perfectly. It also addresses the fine-tuning problem. Why is dark energy's density so small? 120 orders of magnitude smaller than quantum field theory predicts. In Gwendelman's framework, this tiny value emerges naturally from the dynamics of the extra dimensions, rather than being an inexplicable coincidence. Let's step back and appreciate the bigger picture. For decades, string theory was criticized as a theory of everything that predicted nothing. It seemed too flexible, accommodating any observation. But the Swampland program showed that string theory is more constrained than anyone realized. Not everything is possible. Many potential universes are ruled out by consistency, and now, Gwendelman's work shows that within these constraints, our universe, with its peculiar dark energy and inflationary history, fits naturally. This is how science progresses. A theory is proposed, critics identify problems, theorists refine the framework, discovering hidden constraints and new mechanisms. Slowly, the theory becomes more predictive, more testable, more connected to reality. String theory, once floating free in the realm of pure mathematics, is being anchored to the physical universe. Here's a playful analogy. Imagine you're solving a jigsaw puzzle with 10 to the power of 500 pieces. At first, it seems hopeless, but then you discover that most pieces don't fit anywhere. They're malformed, incompatible. The puzzle is actually much smaller. Then someone finds a corner piece, like Gwendelman's dynamical tension, and suddenly sections start coming together. The image begins to emerge. This is where string theory stands in 2025. The landscape is shrinking, the constraints are tightening. And the picture being revealed looks increasingly like the universe we inhabit. So as you rest, consider this. The mathematics of string theory, initially criticized as disconnected from reality, might be more deeply connected than anyone imagined, not because theorists forced it, but because the internal logic of the theory, when fully understood, naturally leads to our universe. In the next chapter, we'll explore another way string theory is being tested, not through cosmology, but through particle physics, where the Large Hadron Collider is hunting for a particle that could either confirm or falsify string theory's predictions. If you're still with me in this late-night exploration, you're part of something rare, a community of curious minds willing to drift through the deepest mysteries of reality itself. A quick subscribe helps others find this peaceful voyage through string theory's hidden dimensions. Now, let's continue into the experimental frontier, where physicists are testing these ideas in the largest machines ever built. Chapter 6, July 2025. The Hunt for the 5-plet. While cosmologists look outward to test string theory through dark energy and the universe's expansion, particle physicists are looking inward, smashing protons together at near light speed, searching for exotic particles that could confirm or refute the theory. In July 2025, a team at the University of Pennsylvania and Johns Hopkins University published results from a search for one such particle, the 5-plet. The 5-plet is a hypothetical particle family predicted by certain extensions of string theory. Its name comes from the way particles transform under the weak nuclear force. They form families, or multiplets, based on their quantum numbers. Most particle families are small. Electrons and their neutrinos form a doublet, a two-member family. The Higgs boson is a singlet, alone. But string theory allows for larger families, including a quintuplet or 5-plet, consisting of 5 related particles bound together by the weak force. Here's the key. String theory, according to some analyses, struggles to accommodate large multiplets. The mathematics becomes strained. Inconsistencies can arise. So if experimenters found a 5-plet particle, it could falsify or at least severely constrain string theory. This is exactly the kind of test critics have demanded, a prediction that could prove string theory wrong. The team, led by physicist Elliot Lapales at Penn and Jonathan Heckman at Johns Hopkins, analysed data from the ATL-AS detector at the Large Hadron Collider. They searched for telltale signatures of 5-plet particles, specifically tracks left by charged particles that suddenly disappear. Why disappearing tracks? Because the 5-plet's neutral member, if it exists, would be nearly invisible to detectors. It would travel a short distance, then decay into other particles, leaving a gap in the data, a disappearing track. The results published in July 2025. No evidence for 5-plet particles was found. The team set a lower limit on the 5-plet mass. If it exists, it must weigh at least 650 to 700 gigaelectron volts, 5 times heavier than the Higgs boson. This rules out lighter 5-plets, but leaves open the possibility of heavier ones at energies the LHC hasn't yet reached. Jonathan Heckman stated, "This early result is already a strong statement. It means lighter 5-plets don't exist." For string theory, this is good news. The theory's Swampland criteria suggested that 5-plets might not be compatible with quantum gravity. If they had been found, it would have created a crisis. Their absence is consistent with string theory's predictions, but the search isn't over. Future colliders, such as the proposed Future Circular Collider, FCC, which would be 3 times more powerful than the LHC, could probe higher energies searching for heavier 5-plets. More importantly, this search exemplifies a shift in how string theory is being tested. Rather than looking for direct evidence of strings, impossible with current technology, physicists are looking for indirect signatures, particles, decays, or phenomena that string theory predicts or forbids. Another exciting possibility involves the 5-plet and dark matter. The neutral member of the 5-plet, if it exists around 10 trillion electron volts, could account for dark matter, the invisible substance making up 85% of the universe's matter. Dark matter's identity remains one of physics' greatest mysteries. We know it exists because of its gravitational effects on galaxies and clusters, but we don't know what it's made of. Dozens of candidates have been proposed: weakly interacting massive particles, WIMPs, axions, primordial black holes, but none have been confirmed. The 5-plet offers a new possibility. If it's real, and if its neutral member has the right properties, it could be dark matter. Discovering it would solve two mysteries at once: the nature of dark matter and a key test of string theory. But there's a deeper lesson here. For years, critics said string theory made no testable predictions. Now, we see physicists at the world's largest particle accelerator actively testing string theory's consequences. They're not measuring strings directly, but they're probing the theory's implications for particle families, decay processes, and symmetries. This is how science typically works. We don't always test theories directly. We test their consequences, their constraints, their predictions. General relativity predicts gravitational waves. We detected them a century later. Quantum mechanics predicts entanglement. We confirmed it decades after Einstein called it spooky action at a distance. String theory is entering this phase. Its predictions about dark energy evolution, particle multiplets, cosmological signatures are being tested, and so far the theory is holding up. Imagine you're a detective investigating a crime. You can't see the culprit directly, but you find fingerprints, footprints, DNA evidence. Each piece of evidence constrains the possibilities, narrows the search. Eventually a picture emerges. This is what physicists are doing with string theory. They're gathering evidence, cosmological observations, particle searches, mathematical consistency checks, and seeing whether the pieces fit together to reveal a coherent picture of reality. As you settle deeper into stillness, imagine the Large Hadron Collider, a ring 27 kilometers in circumference buried beneath the Swiss-French border, smashing protons together 1 billion times per second, searching for particles that could reveal the hidden structure of the universe. Imagine physicists analyzing disappearing tracks, reconstructing particle decays, hunting for signatures that would either confirm or rule out string theory. And imagine the 5-plet, this hypothetical 5-member family, either hiding at energies beyond our reach or perhaps not existing at all. Its absence itself a clue about the nature of quantum gravity. In the next chapter, we'll explore another dimension of string theory's evolution, how artificial intelligence is revolutionizing the way physicists explore the theory's vast landscape, making calculations that once took months take mere seconds. Chapter 7: AR. Cracks the code, machine learning and Calabi-Yau manifolds. For decades, one of string theory's greatest challenges has been computational. The mathematics is staggeringly complex. Calculating the properties of Calabi-Yau manifolds, the 6-dimensional shapes that determine the physics of our 4-dimensional world, requires solving equations so intricate that even the world's best mathematicians can only handle the simplest cases. But in 2024 and 2025, artificial intelligence changed the game. Physicists at the University of Oxford, led by André Constantin, trained neural networks to solve problems in string theory that were previously intractable. They published results showing that machine learning can reduce the time needed for string theory calculations from months to split seconds. Let's step back and understand the challenge. Calabi-Yau manifolds are complex six-dimensional spaces. Complex here has a technical meaning. They have a structure involving complex numbers with a real and imaginary part. Their geometry determines which particles appear in the four-dimensional world we observe and what properties they have. But there are many Calabi-Yau manifolds. Estimates range from hundreds of thousands to possibly many more. Each one corresponds to a different possible universe. String theorists need to figure out which one describes our universe. To do this, they must calculate the metric of each manifold, a mathematical function that encodes distances, angles, curvatures. This metric determines physical quantities like particle masses and force strengths. Calculating a Calabi-Yau metric is extraordinarily difficult. The equations involved are nonlinear partial differential equations with no closed-form solutions. Even numerical approximations require supercomputers running for months. For years, this was a bottleneck. Physicists could study simple Calabi-Yau spaces, but the realistic ones, those complex enough to produce the standard model, were beyond reach. Enter machine learning. In the early 2000s, physicists Toby Wiseman and Matthew Hedrick showed that neural networks could approximate Calabi-Yau metrics, but the techniques were primitive by today's standards. Modern AI, with its deep learning architectures and vast computational power, has supercharged this approach. The Oxford team trained neural networks on known properties of Calabi-Yau manifolds, teaching the AI to recognize patterns in the geometry. Once trained, the network can predict metrics for new manifolds almost instantaneously. André Constantin stated, "The efficacy of these methods is absolutely staggering. These formulas reduce the time needed for the analysis of string theory models from several months of computational efforts to a split second. This is transformative. It means physicists can now scan through the string landscape efficiently, identifying which vacua produce physics matching our universe. Tasks that were computationally impossible are now routine, but AI is doing more than speeding up calculations, it's discovering patterns humans missed. In one study, researchers used machine learning to identify statistical regularities across the landscape of Calabi-Yau manifolds. They found that certain geometric features correlate with specific particle properties. This suggests that even if the landscape is vast, it might not be random. There might be hidden structure, attractors, in the space of possible universes. If true, this would address one of string theory's biggest criticisms, that it predicts too many possibilities. Perhaps most of those possibilities are unstable or fine-tuned, and only a small subset, the attractors, are realized in nature. Another exciting development involves combining AI with experimental data. Researchers are training neural networks on observations, like particle masses from the LHC or cosmological parameters from telescopes, and using the AI to search the string landscape for vacua that match. This is a new way of doing theoretical physics. Instead of deriving predictions from first principles, physicists use AI to explore a vast space of possibilities, filtering out those inconsistent with observations. It's reminiscent of how machine learning revolutionized other fields. In protein folding, AI solved problems that stumped scientists for decades. In climate modeling, AI finds patterns in data too complex for traditional analysis. Now AI is transforming string theory. Of course, there are caveats. Neural networks are black boxes. They can find solutions, but they don't always explain why those solutions work. Physicists still need to verify results, understand the underlying physics, and ensure the AI isn't hallucinating patterns that don't exist. But the trend is clear. AI is making string theory more predictive and more testable. By rapidly identifying which parts of the landscape match observations, machine learning narrows the search for the right vacuum, our universe. To lighten the mood, imagine you're searching for a specific person in a crowd of 10 to the power of 500 people. At first, it seems hopeless. But then you get AI-powered facial recognition. Suddenly, you can scan faces in milliseconds, filtering out those who don't match. The search is still vast but manageable. This is what AI is doing for string theory. It's turning an impossible search into a difficult but solvable one. There's another angle. AI might discover new mathematical structures within string theory. Just as AlphaGo found novel strategies in the ancient game of Go, neural networks trained on string theory might discover new compactifications, new symmetries, new connections that human mathematicians haven't seen. This could accelerate progress dramatically. String theory has always been limited by human ingenuity, the ability of mathematicians to solve hard equations and physicists to interpret results. AI removes some of these limits. As you drift into rest, picture this: vast servers humming with neural networks trained on the mathematics of extra dimensions, scanning through countless geometric shapes, searching for the one that matches our universe. Imagine artificial intelligence, a creation of human minds now exploring the deepest questions of reality. Questions about strings, dimensions, the fabric of space-time itself. And imagine physicists armed with these new tools, finally within reach of a goal pursued for a century, a theory that unifies all forces, explains all particles, and reveals the fundamental structure of everything. In the next chapter, we'll confront the ultimate test: black holes, where gravity is strongest and quantum effects most dramatic, and where string theory makes its most daring predictions. Chapter 8: Black Holes and the Information Paradox. If string theory is correct, it must explain black holes. Black holes are where Einstein's general relativity reaches its limits. At the event horizon, time slows to a crawl. At the singularity, the center, space-time curvature becomes infinite, and Einstein's equations break down completely. This is where quantum gravity is essential, and it's where string theory makes some of its boldest claims. The central puzzle is the black hole information paradox, one of theoretical physics' deepest mysteries. Here's the problem. Quantum mechanics says information cannot be destroyed. If you know the quantum state of a system perfectly, you can, in principle, evolve it forward or backward in time, predicting the past or future. Information is conserved, but black holes seem to violate this. When an object falls into a black hole, it seems to vanish from the universe. All its information, the quantum states of every atom, disappears behind the event horizon, irretrievable. Worse, in the 1970s, Stephen Hawking discovered that black holes aren't entirely black. They emit thermal radiation, now called Hawking radiation, due to quantum fluctuations near the horizon. Over immense timescales, a black hole radiates away its mass and eventually evaporates completely. When it's gone, what happens to the information of everything that fell in? Hawking argued it's lost, destroyed, erased from the universe forever. But this contradicts quantum mechanics. Quantum theory demands that information is preserved. If black holes destroy information, then quantum mechanics is fundamentally wrong. This is the information paradox. For decades, physicists debated whether information is lost, violating quantum mechanics, or preserved, but in ways we don't understand. String theory offers a resolution. In string theory, black holes are not mathematical singularities, points of infinite density where physics breaks down. Instead, they're made of strings and brains, higher dimensional objects, woven into intricate configurations. When an object falls into a string-theoretic black hole, its information isn't destroyed. It's encoded in the quantum state of the strings composing the horizon. As the black hole evaporates via Hawking radiation, the information is slowly released, encoded in the correlations between emitted particles. This is the holographic principle, one of string theory's most remarkable insights. The idea, proposed by Gerard 't Hooft and refined by Leonard Susskind, is that all the information inside a black hole is encoded on its two-dimensional surface, the event horizon, like a hologram. A hologram is a flat image that encodes three-dimensional information. Similarly, the horizon is a two-dimensional surface encoding the three-dimensional or higher dimensional interior. String theory makes this idea concrete. It shows how the information is stored on the horizon and how it's released as the black hole evaporates. This has been tested, at least theoretically, through calculations in string theory. Physicists computed the entropy, a measure of information, of certain black holes in string theory, and found it matches the Bekenstein-Hawking formula derived from thermodynamics and general relativity. This is remarkable. String theory, starting from completely different principles, vibrating strings in 10 dimensions, reproduces a result that had been known from black hole thermodynamics. This is a consistency check, a sign that string theory is on the right track. But there's more. In 2020, a breakthrough occurred. Physicists studying a toy model of quantum gravity, the SYK model, which has connections to string theory, showed explicitly how information escapes from evaporating black holes. They calculated the Page curve, a graph showing how information leaks out, and found it matches what quantum mechanics predicts. This was a landmark. For the first time, physicists could follow information as it entered a black hole, became scrambled, and eventually escaped through Hawking radiation. The calculations used techniques from string theory, particularly the ADS/CFT correspondence, a duality relating quantum gravity in a curved space, ADS, or anti de Sitter space, to a quantum field theory on the boundary. ADS/CFT is one of string theory's crown jewels. It's a precise mathematical equivalence. Calculating something in gravity is the same as calculating something in a boundary field theory. It's like having two languages that describe the same reality. Using ADS/CFT, physicists can study black holes in quantum gravity by translating the problem into a quantum field theory, where calculations are easier. Then they translate the results back. Through this method, they showed that information is preserved in black hole evaporation, resolving the paradox. Stephen Hawking, before his death in 2018, conceded that information isn't lost. He had changed his mind based on string theory's insights. Let's step back and appreciate what this means. Black holes are the most extreme objects in the universe. They're the arenas where quantum mechanics and gravity clash most violently. If string theory can explain black holes, preserving information, calculating entropy, describing their quantum states, then it's a strong indication the theory is correct. Now imagine the event horizon of a black hole as a vast shimmering membrane. Every particle, every photon, every atom that falls in leaves a mark on this membrane, a ripple, a distortion, an encoded bit of information. As the black hole slowly evaporates over trillions of years, The membrane glows faintly with Hawking radiation. Embedded in this glow are the quantum correlations carrying the information outward, restoring it to the universe. From outside, it looks like information vanishes, but from the perspective of string theory, it's merely transformed, hidden in the subtle correlations between particles streaming away. This is one of string theory's most beautiful predictions, that the universe is fundamentally holographic, with information about volumes encoded on surfaces, and that nothing is ever truly lost, only transformed beyond easy recognition. As you close your eyes and settle into the night, imagine a black hole far away, slowly radiating, its event horizon a tapestry of quantum information woven from strings. Imagine the information of a star that collapsed 1 billion years ago, now being released particle by particle, encrypted in Hawking radiation, drifting through the cosmos. And imagine string theory connecting the smallest scales, vibrating strings, to the largest and most mysterious objects in existence, weaving a story that preserves the fundamental laws of quantum mechanics even at the edge of space-time itself. In the next chapter, we'll explore the philosophical implications of string theory, what it means for the nature of reality, the multiverse, and our place in it. Chapter 9. The Multiverse and the Nature of Reality. If string theory is correct, it might imply something both wondrous and unsettling, that our universe is just one of many, perhaps infinitely many universes, each with its own laws of physics, its own particles, its own constants of nature. This is the multiverse, and it's one of string theory's most controversial implications. To understand how string theory leads to a multiverse, we must return to the landscape of vacua. As we've discussed, the extra dimensions in string theory can be compactified in many ways. Different Calabi-Yau shapes produce different four-dimensional physics. With perhaps 10 to the power of 500 possible shapes, this suggests 10 to the power of 500 possible universes. Each one is a solution to string theory's equations, each one is mathematically consistent, and each one might exist somewhere. But where? The idea of eternal inflation provides a mechanism. Inflation is the theory that the early universe underwent a period of rapid exponential expansion, driven by a scalar field called the inflaton. As this field rolled down its potential energy curve, different regions of space could end up in different vacua. Imagine soap bubbles forming from churning foam. Each bubble is a universe, a region of space where the inflaton settled into a particular vacuum. These bubbles are causally disconnected. Light hasn't had time to travel between them. From inside one bubble, you can't see the others. In eternal inflation, this process never stops. New bubbles form continuously, each one a universe with potentially different laws of physics. The multiverse is an ever-expanding froth of universes, each one experimenting with different possibilities from the string landscape. This idea is simultaneously fascinating and troubling. It's fascinating because it answers a deep question. Why are the constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, the values they are? In a single universe, these constants seem arbitrary, fine-tuned. Change the electron mass by a few percent and chemistry collapses. Change the strength of gravity and stars can't form. Our universe seems precisely calibrated for life, a coincidence so improbable that it demands explanation. The multiverse offers an answer. Every possible set of constants exists somewhere. We find ourselves in a universe with constants that allow life because, obviously, we couldn't exist in universes where life is impossible. This is the anthropic principle, not that the universe was designed for us, but that selection effects explain why we observe what we do. But many physicists find this deeply unsatisfying. Science aims to predict, not just explain after the fact. If string theory predicts a multiverse where anything is possible, then it predicts nothing. Leonard Susskind, who coined the term landscape, embraced the multiverse. He argued that the fine-tuning problem is real and the anthropic principle is a valid scientific explanation. Others, like David Gross, resisted. He called the anthropic principle giving up, and hoped for a deeper theory that would uniquely predict our universe. This tension remains unresolved. But here's a twist. Recent work suggests the landscape might not be as anarchic as feared. The Swampland program has shown that many vacua are actually inconsistent. The landscape is smaller than 10 to the power of 500, and within the viable vacua, there might be patterns, attractors, or selection principles that favour certain types of universes. If so, then string theory's predictions become more definite. It's not that anything goes, but that only certain regions of the landscape are accessible. Furthermore, even if the multiverse exists, it might leave observable signatures. Collisions between bubble universes could create patterns in the cosmic microwave background, the afterglow of the Big Bang. Anomalies in the distribution of galaxies might hint at the influence of nearby universes. These are speculative, but they're testable. Now let's consider the philosophical dimension. If string theory and the multiverse are real, what does it mean for our understanding of existence? First, it suggests that reality is far larger and stranger than we ever imagined. Our universe, everything we can see, from the smallest quark to the largest galaxy cluster, is a tiny bubble in an infinite ocean of universes. Second, it implies that the laws of physics are not unique or fundamental. They're emergent, contingent on which vacuum we inhabit. In other universes, electrons might have different masses, gravity might be stronger, space-time might have different numbers of dimensions. Third, it raises questions about meaning and purpose. If every possibility is realized somewhere, does any particular outcome matter? If there's a universe where you made every different choice, where history unfolded in every conceivable way, does your life have unique significance? These are not scientific questions in the narrow sense, but they arise naturally from string theory's implications. String theorists are divided. Some embrace the multiverse, finding beauty in its vastness. Others hope it's wrong, that deeper principles will emerge to select a unique universe, ours. Let's slow down and consider a gentler perspective. Perhaps the multiverse, if real, doesn't diminish meaning but expands it. Every possibility, every potential, every path, realized somewhere. The universe is not a single story but an infinite library of stories, all equally real. From this view, our universe is special not because it's unique, but because it's ours, the one we inhabit, the one where we ask these questions. And the quest to understand string theory, to test its predictions, to probe its implications, that quest is itself meaningful, regardless of how many universes exist. We are the part of reality that wonders about itself, and that wondering is a profound thing. As you drift into stillness, imagine the multiverse, an endless expanse of universes, each one a bubble in the quantum foam, each one governed by different laws. Some lifeless, some teeming with unimaginable forms of complexity. Imagine strings vibrating in 10 dimensions, their patterns generating universes like ours, like nothing we can conceive, everywhere, always. And imagine yourself here now in this particular universe, contemplating the vastness, asking whether we're alone or whether reality is an infinite garden of possibilities. In the final chapter, we'll bring it all together. Where does string theory stand now? What's next? And is this truly the theory of everything, or a step towards something even deeper? Chapter 10. Is string theory real? Where we stand, and what comes next? After 50 years, trillions of dollars, thousands of papers, and countless careers, where does string theory stand? Is it the theory of everything, the ultimate description of reality? Or is it a magnificent detour, a beautiful mathematical structure that doesn't actually describe our universe? Let's take stock honestly. What string theory has achieved? First, it's the only known consistent framework for quantum gravity. Every other approach, loop quantum gravity, asymptotic safety, causal set theory, faces mathematical challenges that string theory avoids. It might not be right, but it's mathematically complete in a way no rival is. Second, it unifies forces and particles. Gravity, electromagnetism, the weak and strong nuclear forces all emerge from vibrating strings. There's no need for dozens of fundamental particles, just one object, vibrating in different modes. Third, it explains black hole entropy. String theory reproduces the Bekenstein-Hawken formula for black hole entropy from first principles. This was a stunning success, showing that string theory captures essential features of black holes. Fourth, it resolves the information paradox. Through the holographic principle and ADS/CFT duality, string theory shows how information escapes from evaporating black holes, preserving quantum mechanics. Fifth, the 2024 to 2025 breakthroughs have brought string theory closer to observation than ever before. The bootstrap results show it's mathematically inevitable. The DESI Dark Energy observations align with its predictions. The Swampland program narrows its landscape, making it more predictive. AI is accelerating calculations, making testable predictions feasible. What remains uncertain? First, we still don't know which vacuum describes our universe. With a large, though shrinking landscape, identifying the right compactification is a monumental task. Second, supersymmetry hasn't been found. String theory requires it, but no superpartners have appeared at the LHC. Either they're heavier than we can reach, or something is wrong. Third, direct evidence for strings remains elusive. We can't probe the Planck scale. We're testing consequences, indirect signatures, but we haven't seen strings themselves. Fourth, the multiverse question is unresolved. Does string theory imply many universes, or is there a selection principle that picks out ours uniquely? Fifth, string theory is incomplete. We don't have a fully non-perturbative formulation. We understand strings in certain regimes, but not all. There's likely a deeper structure, sometimes called Chna theory, that we've only glimpsed. Where do physicists stand? The community is divided. Some, like Edward Witten, Brian Greene and Juan Maldacena, remain confident that string theory is the right path. They point to its mathematical beauty, its consistency, and its successes in black hole physics. Others, like Lee Smolin and Peter Voigt, remain skeptical. They argue that 50 years without experimental confirmation is too long, that resources would be better spent on alternative approaches. A third group takes a pragmatic view. String theory is a powerful tool, useful for understanding quantum gravity and generating insights, even if it's not the final theory. The truth might lie in between. Perhaps string theory is correct but incomplete, a low-energy approximation of something deeper. Just as Newton's gravity is correct within its domain but gives way to Einstein's relativity at higher precision, string theory might give way to a more fundamental theory. Or perhaps string theory is one facet of a larger framework, a piece of a puzzle that also includes loop quantum gravity, holography, and concepts we haven't discovered yet. What comes next? In the near term, several avenues are being pursued. 1. Cosmological observations. Future telescopes. NASA's Nancy Grace Roman Space Telescope, launching 2027, and the Vera C. Rubin Observatory will measure dark energy's evolution with unprecedented precision. If dark energy continues to weaken, string theory's stock rises. If it remains constant, other models gain favour. 2. Particle collider searches. The LHC will continue running, searching for superpartners, extra dimensions and exotic particles. Proposals for a larger collider, the Future Circular Collider, would probe higher energies, possibly finding evidence for string theory's predictions. Number 3. Gravitational wave astronomy. Detectors like LIGO and the planned LISA space interferometer might detect signatures of cosmic strings, defects in spacetime from phase transitions, or other string-theoretic phenomena in gravitational waves. 4. Quantum gravity experiments. Tabletop experiments are being designed to test quantum gravity effects at small scales, entangling particles through gravity, detecting quantum fluctuations in spacetime. These won't probe the Planck scale directly, but they might reveal hints of quantum gravity's structure. 5. Mathematical progress. Advances in understanding the landscape, the swampland, and the constraints on string theory will sharpen predictions. AI will continue accelerating calculations, helping identify which vacua match observations. A thought for the future. Perhaps in 50 years, string theory will be vindicated, its predictions confirmed, its framework accepted as the true description of reality. Or perhaps it will be seen as a stepping stone, a necessary detour on the path to something we can't yet imagine. Either way, the journey has been extraordinary. String theory has transformed how we think about space, time, particles, and forces. It's shown that mathematics can guide us toward truths about nature that experiments can't yet reach. It's reminded us that the universe is stranger, deeper, and more beautiful than our everyday experience suggests, and it's inspired a generation of physicists to ask the boldest question of all: is everything, every particle, every force, every dimension, part of a single unified whole? Is there one equation, one principle, one structure from which all reality flows? Einstein dreamed of this. He called it a unified field theory. Today, we call it a theory of everything. String theory is our best attempt. Whether it succeeds or not, the quest itself is a testament to the human spirit, the drive to understand, to unify, to glimpse the ultimate nature of existence. As you rest now, let this journey settle gently in your mind. Strings vibrating in hidden dimensions, extra spaces curled beyond sight, black holes preserving information, dark energy shaped by geometry, the multiverse unfolding in infinite bubbles. Whether string theory is the final answer or a chapter in a longer story, it represents something profound. The possibility that reality, beneath its apparent complexity, is simple. That the universe is not chaos but symphony. That the fabric of existence is woven from a single thread. Einstein died before finding his unified theory, but his dream lives on, pursued by physicists who peer through mathematics into the structure of reality itself, and perhaps, one day, we'll know. The theory of everything will be confirmed, and the universe will reveal its deepest secret, that it is one. Until that day, we search, we calculate, we wonder. We test predictions, refine theories, and follow where the mathematics leads. This is science at its most audacious. This is humanity at its most curious. This is the quest for string theory, the first evidence after 50 years, and the dream of understanding everything. And as we reach the edge of this contemplation, take a moment to let the vastness breathe through you, from Einstein's unfinished dream to the 2025 breakthroughs, from vibrating strings to dark energy's whisper. We've journeyed through one of humanity's most ambitious quests, the search for a theory of everything. If this exploration has stirred a quiet sense of wonder within you, I invite you to linger in that feeling. Subscribe to continue these nocturnal voyages through physics' deepest mysteries, or simply drift into rest, knowing that the universe reveals itself slowly, one insight at a time. This is Sleep Entangled, where mathematical beauty and cosmic mystery merge into understanding. Until we meet again beneath the vast tapestry of reality, rest easy in the knowledge that strings, if they exist, are vibrating right now, weaving space and time and matter into the present moment you inhabit. The theory of everything awaits, and we're closer than we've ever been.